In continuation to the previous lecture, which was delivered on the topic uncertainty principle, we'll continue to that. Now today we'll discuss the topic to be discussed today will be the derivation from wave packet impossibility of a particle following a trajectory. Number one. Number two is estimating minimum energy of a confined particle using uncertainty principle, and number three is energy time uncertainty principle. So these are the three topics which we'll discuss today. Now, as far as the first topic is concerned, what we know so far is from the uncertainty principle that del x del px, uncertainty in position and momentum. This relation we already have this particular relation, which is greater than equal to h cross by 2 or h by 4 pi. Now what we know so far is that if something is been allowed to, now if you want to isolate a particle and want to see it, okay, the problem is that when we allow when we would like to visualize the particle, we always need a light to illuminate it, and when we illuminate the particle, the photon will strike the particle, and obviously that will change the momentum. So this will not happen in the case if we'll assume, say for example, if we'll take a tennis ball or any other ball and if we'll allow the photon to strike the ball, you don't find that such thing will happen, because the size of the ball is too big for a photon to make any appreciable change in the trajectory of the ball. But as far as particle like electron is concerned, when a photon strikes, okay, a particle, okay, so what will happen, say for example electron, is that until unless it is illuminated by a photon, you won't be able to look at its position. So once you want to look at its position, you allow the the photon to strike the electron, and as the electron strikes the photon, as the photon strikes the electron, the position or the momentum of the electron will change, and obviously that will change the trajectory. So as it has been written in the first part, that derivation from wave packet impossibility of the particle, so that becomes very, very clear now that it is impossible to make it show where the particle will be as the photon strikes the particle. So the trajectory followed by the particle is rather impossible to be traced out. Number two is estimating minimum energy of a confined particle using uncertainty principle. Now we consider a particle of mass m confined in 3D box of length L, free to move within the box, or taking the uncertainty in position in 1D, okay, taking the position uncertainty in position in 1D, its RMS deviation, its root mean square deviation delta x will be given by minus this much, which is nearly equal to this much. Now a free particle which is constrained between x equal to 0, but we will now assume that it is confined between x equal to 0 to x equal to L, has a distribution function, distribution function which is a constant, okay. So the relationship for the standard deviation of the position is the square root of the integral, okay. Now that integral is given by 0 to L x minus value of x whole square dp by dx into dx, which is equal to again 0 to L x minus x whole square k dx. Now normalizing the distribution function, normalizing the distribution function or rather distribution, we get z dual k dx equal to 1, which is equal to obviously k into L. Therefore k will be equal to 1 by L. Therefore mean value of x is 1 by L 0 to L x dx, which is equal to L by 2. So this is what you will get. Now sigma is equal to x minus x, and we'll take this much whole square, which is given by x square plus L square by 4 minus Lx minus Lx minus Lx. Okay, so it's like this. So now it will be 0 to L, the limit x square plus L square by 4 minus Lx dx is equal to L square by 12, or sigma is equal to under root L square by 12, which is equal to L by root 12. Uncertainty in momentum, uncertainty in momentum is del px greater than h by 2 del x, or del px equal to h by root 12 by 12. So the average kinetic energy can be expressed in terms of the average of the momentum squared, okay, which is related to the uncertainty in momentum by del p equal to okay. So it's like this. This is the relation, which is, or del p equal to, it will be del p square rather equal to this much as del p is equal to 0. So the average momentum is 0, as the average momentum is 0 for free, average momentum is 0 for free random motion of the particle in the box. The y and z component, are equivalent. So average kinetic energy can be expressed as kinetic energy minimum is equal to, which is equal to px square plus py square plus z square by 2m, which is given by 3 px squared. So the value is obviously the same. Now substituting the value of px square, we'll get 3 delta, rather this px square can be written like this, delta px square by 2m. Substituting the value of delta px, which we have earlier find out, it will be 9h square by 2m L square, which is the minimal value of the kinetic energy. The third part we have mentioned already is energy, time, uncertainty principle, the third part. So as far the third part is concerned, what we know is that it is the another form of uncertainty principle, energy and time. So we might want to measure the energy E emitted during the interval delta T, in the energy emitted in the time interval delta T in an atomic process. If the energy is in the form of electromagnetic waves, the limited time available restricts the accuracy with which we can determine the frequency of the wave. Okay. Now we assume that the minimum uncertainty in the number of waves we count in a wave group is one wave. Now since the frequency of the wave under study is equal to the number of them we count divided by the total interval, the uncertainty delta f in our frequency measurement is delta f greater than equal to 1 by delta t. Now what delta f 1 by delta t? Now what happens is this. Now the corresponding energy uncertainty maybe it's given by delta E is equal to h delta f, and so delta E is equal to greater than equal to h by delta t or delta t rather, h delta t greater than equal to h. So a more precise calculation based on the nature groups changes this result, and we will get delta E delta t greater than equal to h cross by 2. So this is the third part, and with this we conclude the syllabus related to semester 4 CVCS part. As far as uncertainty principle is concerned, in the next lecture we'll move ahead. Thank you very much.